Okay. So in spherical coordinates, Laplace highlighted here represent the angular part of the Laplacian equation, which depends on theta and the phi. Now the method in which we try to seek the solution of the following kind. Now if I rearrange my Laplace equation to apply, and if you will
No,
look
no,
at this
Devang.
equation,
Your voice is breaking a lot. वो बीच में चला जा रहा है बार बार. There's a problem with your internet. Maybe.
is it fine here?
Yeah, it's fine. Yes, Devang, it was fine. Go on.
Okay. So I was saying when we apply the method of separation of variable in Laplace equation, then it takes the following form. And if you will look at this equation, this kind of equation can only be satisfied because we can see that the first term here depends only on r and the second term depends on theta and phi. Now, this kind of equation can only be satisfied if each term is a constant. Thus, we can write it this following way. Now, I want to find this f, which is our function of theta and phi, because radial part will be easy to solve. But if you will look at that angular part, that is our main goal today's talk to solve. Now, I wish to find the general solution of this equation, which is nothing but the rewriting of my equation 2. And if somehow I was able to find such a function f, then I can say that f is an eigenfunction of the operator, that is our angular Laplacian, with eigenvalue c theta. And now such a function of angle can equivalently also be thought as a function of, you can say, unit vectors that points along the theta, r, and phi. And such a unit vector can be written as the following way, where E1, E2, E3 hat can also be rewritten as EX hat, EY hat, and EZ hat. But I am labeling the unit vector using the number 1 to 3 because I think that when we are summing over the indices, it will be useful. Otherwise, you can also use EX, EY, EZ. Now, here comes the claim that such a function of angle can be written as the power series in terms of n hat, or more precisely as a power series in components of n vector. Now I am not going to prove this thing, but it is at least true for square integrable functions. And such a power series will be written as the following way. If you will look at this equation, here the repeated indices are sum from 1 to 3 as a Cartesian coordinate, and the term that you can see at the last is the most general term in the series. And the first three terms correspond to L is equal to 0, 1, and 2. And the indices here represent the L different indices like I, J, and etc. And since they are repeated here, they can be each term from 1 to 3. Now, if you will look at the coefficient here in this equation, they are called the tensors, which you can see that C0, C1, C2, etc. These are the tensors. And the number of indices is called the rank of the tensor. And the tensor we are talking in this case are the special cases of tensor, although they can also be treated as a scalar, vector, and matrix. Now it is possible to impose a restriction on this coefficient of this equation without actually restricting what appears on the right hand side. But before going to that, let us talk about this tensors more. Now these tensors are symmetric in the sense that any reordering of indices give us the same thing, where J1, J2, JL are the different permutations of this I1, I2, and IN. And the tensors are traceless in the sense that if any two indices are set equal to each other and then sum, the result will be equal to 0. And since we have already assumed it to be symmetric, then it doesn't matter that which indices are set. So we can choose the last two also. Now to explain why this restriction of CS here does not impose any restriction or use the example of R rank 2 tensor. But you can easily see that the same argument applies for all kinds of Ls. This can be seen that here the rank 2 tensor is symmetric, which makes no difference on the right hand side if we impose any kind of restriction on it. Because this tensor is multiplied with the unit vector, which you have seen in this equation. That is here. Rank 2 tensor you can say is multiply with the unit vector that are C n at I and at J. So if this tensor is antisymmetric, then it will not contribute to right hand side of our equation that we have shown earlier. And the requirement of tracelessness is less obvious. But suppose that our tensor is not traceless, then we can write it in the following way, where same indices represent that we are talking about the diagonal elements here. And if it is not traceless, then it will have some value lambda. Now, here I define a new quantity in terms of older quantity, which is nothing but the older quantity and difference of the 1 by 3 times lambda times that delta function. Now here delta function you can also think as a matrix if you are having a problem in understanding the trace of delta function. And you can see that the trace of a delta function, if I talk in Cartesian coordinates, will be 3 because we are dealing with the I, J, and K. So the trace of delta function will be 3. That is why I have to compensate that I have created that 1 by 3 quantity here. Now, since this tensor is traceless, that we can show that this thing that we defined earlier now, that new quantity will also be equivalent to 0. Where I just write the original term in terms of this new term. And I use the fact that the delta function times this unit vector will be equal to 1. Since now n hat is a unit vector, then the extra term here can be easily absorbed using the redefinition of our rank 0 tensor, which you can see in the following way. Now, when I have defined these new terms, then I can write my older expansion that I have shown you earlier in terms of these new terms that I defined now. And you can see that the tensor that multiplies from by our unit vector is traceless with no restriction on what function can be expressed in this form. Now I want to evaluate the L term of this expansion, because if I was somehow able to evaluate the angular Laplacian for L term, then I can easily do that for further terms. Now to evaluate it, and you can see that bottom I have also written that the L term is given by this following equation. So you can easily refer it. Now to evaluate it, I am going to use a convenient trick. Instead of going to deal directly with this L term, here I am going to introduce a radial variable that is r, and I am going to define it in coordinate vectors. Now here I have also used the notation of Griffiths, so you can check. I think it's equation 1.219 in his book, so you can easily refer it. Now I will denote the Cartesian coordinate by the x, y, and z, and I will denote it in index notation in the following way using x sign. Now of this form can be expressed in terms of this r. So here I have defined the old r L term in terms of n hat, in terms of now r vector. You can say that here I have multiplied it with that r vector. Now to evaluate our L term, I will start with putting the values of L, and I will start with L is equal to 0. And here CL is same as rank L tensor that we used earlier for defining our new quantity in terms of R vector. Now I am going to use equation 1, which relates the full Laplacian and the angular Laplacian, and we will find that in this case, the full Laplacian radial derivative piece of equation 1 will both be simple. So it is easier to now determine the angular Laplacian. Earlier, it will be very cumbersome if we do the algebra in older form. Now we will start with plugging the values of different L, and I will start with L is equal to 0. So for L is equal to 0, you can clearly see that the first term is constant, so its derivative will be 0. Now similarly for L is equal to 1, since the first term gives us a constant and the second derivative easily vanishes, then the first that L is equal to 1 is also going to give the same value, that is 0. Now the first non-trivial case will come when we will talk about L is equal to 2. And if we compute it for L is equal to 2, then you can easily say that due to some term that symmetrize in I, J, and K and delta function, it will be also equivalent to 0. Now from here, I can easily generalize this to L term, and I can say that this L term will also be 0. Now if you want to check this, you can check for L is equal to 3 also. Then also when you will compute the derivatives, you will get some delta function times xj, xk, and some symmetric part. So you are also going to get for L is equal to 4, 5, 0 only. Now in last step, I use the only fact that our tensor that we are using is traceless. Now, talking about the general term, one can easily see that after derivatives are calculated, there are L minus 2 factors of x side that remain, but there are still L indices on our tensor. Since the indices are summed from two indices on this tensor, we can easily contract it. And from contraction, I mean that they are set equal to each other. And then when I summed it here, they call the result L to be vanished. So you can easily see that in this way also our L term is going to be 0 only. Now to see that what this says about here we have find the L term in terms of R vector, you can see. But we want to find it in terms of n head. So in order to find it in terms of unit vector n, we have to see that what this equation says. Now we can say that we have earlier how we have defined this equation. And in order to find the solution in terms of n head, we are going to use equation 1. Now if I plug the values in equation from this to equation 1, then you can easily say that we are going to get the following kind of calculations. And if one will do this calculation in terms of n head, then you can easily find that our L term of acting on this angular Laplacian will give us the following values. Now we have found a very useful result because we have found the angular eigenfunction and the eigenvalue of our differential operator that we defined earlier. Now using this eigenfunctions and eigenvalue, we can easily find the general solution of Laplace equation in spherical coordinates. In order to find the general solution of Laplace equation in spherical coordinates, we are going to return this solution to the Laplace equation in separation of variable form. And if we do thus, so we know that the C theta can only take the values that are minus L and L plus 1, where L is any integer. And if we plug this value, our equation 3 will become such kind of a differential equation, which will be a second order differential equation. Now this kind of equation is very easy to solve. We can easily try a solution of a form of this form. And when we plug this solution in this equation, we will get the following equation, which is nothing but a quadratic equation with two roots, p is equal to L and p is equal to minus L plus 1. And we have found a two solution for a second order linear differential equation. Now we know that any solution can be written as a linear sum of these. Thus, we can write it in the following way. Now, allowing different values of AL, DL, we can write the general solution of Laplace equation in spherical coordinates. And it will be the following of this equation. And we have found the general solution of Laplace equation in terms of our traceless symmetric tensors. Now in next talk, I will show you how that later L term here, when compared to standard expression in spherical harmonics, correspond to the sum of all the terms with same L but not for L. And in this equation here, AL and DL are different arbitrary traceless symmetric tensors. Till now, if you have any doubt, you can ask. Is anybody having any doubt?
Yeah, so your C has this value of L plus 1. Yes?
What you are saying, please repeat.
No, C has this value of L plus 1, where the L are integers.
Yes. That
So
eigen
in
values.
quantum mechanics, yeah. In quantum mechanics, we have the angular momentum eigenvalues as well, like this, you know, L plus 1.
Yes. There also we use this spherical harmonics at Legendre. Yes.
Yeah. I found it. Yes.
But using Traceless symmetric, you are finding a general solution.
Yeah, I got it. Why only traceless symmetric tensors? Like, why not trace? If you have a trace, you also talked about if you have a trace tensor, you can make a traceless tensor by subtraction of 1 by c.
That I told earlier now. That if you, it is not important to have traceless. You can easily reabsorb it in the form of this traceless symmetric tensor.
But let's say if you do not want to do with traceless, you do not want to go with traceless. If you have some trace, can you not find solutions like this? Phi in terms of trace centers, like fine. Oh, okay.
No, you can. You can find a solution, but you have to redefine all the quantities.
Got it. Then you do not have to minus 1 by 3 lambda delta function.
Yes.
Okay. Can you go to equation number 3? There was an equation number 3 somewhere.
Can you tell me the slide one?
Equation number 3. There was this equation number 3.
This radial part equation.
Yeah.
Yes. Yeah.
How do you solve this?
This is a differential equation you can easily solve. This is a differential equation R only, no?
Oh, okay.
So you can solve, but I am talking about F only because you can see that the function of angle is so much complicated here. You can see that.
Yes, I can see that.
And if you will look at Griffith's book, he does not talk about azimuthal symmetry part, which is related to rotations. So that is why angular part also becomes important.
Yeah.
Yes.
Basically, you have this eigenvalue. Basically, you have this eigenvalue equation. You find the eigenfunctions and you put it in your Laplace equation. You find then the general solutions. Phi. Yes. Basically, you do that.
Yes.
Okay. Yeah. Thank you.
Okay. So in next talk, I will show you how these tensors we described today are related to the spherical harmonic and Legendre polynomials. Okay.
Okay. Next Sunday, you mean?
Yes, I will do that in next talk, and you can find these differences using